I'm Edward Lee. I apologize for not having been here on Tuesday. I was forced to be in New York for a research meeting at IBM, and it couldn't get scheduled any other time, so that's the way it is. But I'm going to be collaborating with Sanjit Seshia on this course, so we're going to be working pretty closely together, and you should feel free to contact any of us, either of us, at any time for any issues. So, you know, it doesn't matter. We've worked very well together for quite some time. Does anybody have any questions about the logistics of the course before I get started into the content? Yeah, question. When are the lab sections going to be finalized? So your responsibility is to coordinate with the GSIs. Dai Bui, is Dai here? No, not here. Or Kevin Weekly, okay? They're handling setting up the schedule. And our plan is to have 3 3-hour sessions, and we've got to pick 3 3-hour slots that work for everybody, subject to some pretty severe constraints, which is that we can't have more than 18 people in any one of the sessions. This is going to be a pretty complicated scheduling problem, okay? And I apologize for that. For some reason, there was some misunderstanding with the registrar, and they didn't create the lab sections for you to sign up initially, which is, you know, how the system is designed to resolve such conflicts. They created 1-hour lab sessions, which is actually not very useful. So we're just going to have to work it out. Yeah, question?
So we don't need to go to that 1-hour session
this week? This week you don't need to, no. We're going to start them next week. But if you haven't got a clear idea by tomorrow of what the possibilities are, was this discussed on Tuesday? No? Okay. All right. I'm going to get after Kevin and Dai right after lecture today and get them on it, okay? Are you all receiving the email for this course? Or let me put it differently. If you haven't gotten any email from me on this course, okay, then you're not receiving email, and it's going to be very difficult to communicate with you. And you need to follow the instructions that are on the home page for the course, which is to verify your bspace account setup. Okay? In particular, unfortunately, since rather recently, bspace by default, in honor of all of your privacy issues, by default masks your email address, and consequently we can't send you email unless you explicitly unmask it in this project. So we do kind of need you to be able to, I mean, we do need to be able to communicate. We will use the website as a backup, so if for some reason you can't set up bspace to get email, okay, then you're responsible for checking the website on a daily basis, okay? That's the trade-off. Okay, so I think that the way that they're planning to do this is to set up a doodle poll, okay, set up some lab sessions, and then tell you which lab session that hopefully works for you also works for them, okay? Try to give them as many possibilities as possible, because otherwise we have, you know, a rather difficult logistical problem. So the labs will start next week, and the lab next week is going to be kind of an introduction to LabVIEW. There is a problem set assignment that is posted. If you go to the master map of the course, which will evolve as we go, is this one. If you follow the lectures link, okay, the dates are here. Today is the 20th, and homework 1 is out. You can follow that link, and it tells you what the homework assignment is and when it's due. Okay, it'll be due Monday, February 1st. We may postpone that until Wednesday, but don't count on it. But what the criterion will be, if we manage to get all the labs sorted out, then it'll be due Monday. Okay, if we have trouble getting the lab set up, we'll give you a little more time, because the first week of lab is an orientation on LabVIEW, which is required for one of the problems in the homework, problem 6, okay? Some of you, I think, have already used LabVIEW. If you took EECS 20 anytime recently, for example, you have that experience and you wouldn't have any difficulty doing this homework right away. But we don't assume that you do, and consequently, the first week of lab is kind of devoted to giving you access to that tool in a workable way. Yeah, question?
Do we submit the homework on vSpace?
You submit the homework on vSpace. I don't know. We have to figure that out. We'll let you know before February 1st how to submit the homework. Anything else? Okay. So I wanted to start today by showing you inspirational video, okay? And the goal of showing you this video is to kind of give you a sense of what I think the technology that this course is about is capable of and why it's really needed, okay? So I'd like to preface this with just a word about, what this is about. In my opinion, what you're about to see is something that your generation is going to make very improbable, okay? It's going to be your generation. You're going to witness a problem now that we have today that is going to be solved. It's going to be solved by you guys. And it's going to be solved using techniques that this course introduces you to, okay? So let's have a look at this video. This is a webcam that's capturing traffic flow on a highway. This highway is actually in Southern California, so it looks like a pretty normal day until that happens. Okay? So, not good, right? I'm convinced that before too long, people will look back, you guys will look back on a video like this and say, how could engineers field a product, a truck, that would do that? Okay? We shouldn't. We actually have the technology in a certain principled way to make trucks that won't do that. No matter what the driver does, they won't do that. Okay? Who knows what the driver did? The driver didn't survive. Might have fallen asleep, might have had a heart attack. Who knows, right? This course is about the kind of technology that it takes to make trucks that won't do that, okay? And what does that involve? Well, it's not just the computing. It's not just the sensing. It's not just the physical dynamics of how you control where a vehicle goes. It's the combination of all of those things, okay? So we use the term cyber-physical systems to talk about that interaction, that overall dynamics that combines what the physical devices do, the trucks, the dynamics of the truck, okay? The dynamics of the sensors, how do they measure the physical world around them? What the software does with the information that's given to it by the sensor, how that software then affects the actuators, which will control what the truck does, okay? And how the overall system behaves, and how the overall system behaves in the presence of faults. What if the sensors fail, okay? You have to be able to design systems that can tolerate that kind of thing, okay? So what we mean by cyber-physical systems is that overall closed-loop conjunction of software, networking, sensors, actuators, and physical processes, okay? Now, one of the problems, of course, with designing a course around that concept is that, well, basically we could take all of EECS, mechanical engineering, if you apply it to bio applications, bioengineering, and say, well, okay, you guys need to know all of that stuff before you take this course, okay? everything offered by this department, MECI and BioE is a prerequisite. Okay? Well, that's not going to work, right? Obviously. But in a sense, engineers who design the kinds of systems that we're interested in actually face that problem. They're constantly confronted with having to understand things that they're not actually trained in, okay? Part of that, of course, is learning to collaborate with people who do know about the things you need to know about. One of the things we try to do in the projects for this course is to encourage you, don't make teams with your buddies who have taken all the same classes you took, okay? You're going to get a much better project if you make teams with other people who have taken classes you never even heard of, okay? If you can form teams that are more complementary, right, so that you can divide the labor. One guy can focus on the properties of the sensors. Another guy can focus on whatever mechanical parts might be needed. Another guy can focus on the networking. Another guy can focus on the signal processing, right? If you make your teams complementary, you'll get much more interesting projects. I'd like to encourage you to take a look at the videos of previous projects, okay, to give you kind of inspiration. In my experience, so there's links to those videos somewhere. Yeah, right here. When we do the project presentations at the end of the course, we ask your permission and say, would you like us to be able to record your project presentation, and if so, can we put it on the web? And so far, everyone has said yes. You're under no obligation to say yes, of course, but as a consequence, your predecessors in this class have agreed to, have their project presentations visible, primarily to give you guys inspiration. By the way, you can totally redo one of their projects if you think, these guys, what they did was kind of cool. You think maybe you can do it better, or or maybe you don't think you can do it better. You just want to replicate it. That's okay too, as long as you don't actually seek out their solution, right? I want you to have the experience of doing the design yourself, okay? But it doesn't. We don't require the projects to be novel, although in my experience, almost all of the projects have been really picked by the team rather than things suggested by us, and they've surprised me with what they tried to do. In some cases, they came to me and said, we want to do this, and I said, no, you're never going to get that to work. And then they got it to work. So, it's, be bold, but be prepared to adjust your plans during the semester, right? You might, in fact, one of the things that we're going to focus on is managing your projects. So you're going to come up with, a statement of what you think you're going to do. Then you're going to revise that statement. Then you're going to revise it again, okay, as you go through the project. Okay, let's see. Because of this cyber physical systems focus, I wanted to just make a point that a class like this, first of all, classes in embedded systems are not very well established these days. There's a lot of institutions that have something that they call this, but the interpretation of what it means is pretty highly variable. At most institutions, what they mean is what's in blue on the left here, which is very much about the techniques that you need to get software embedded into the physical world and interacting with the physical world. It's a how-to class, the tricks and tips, okay? How do you connect up a sensor to a microprocessor? How do you write an interrupt service routine to get the sensor data into your software? How do you process that sensor data? How do you write to a pulse width modulation motor controller to control a motor? How to. We're not going to emphasize the how-to on this course. In fact, we're going to let you guys read up and use the web, use resources to figure out the how-to. We'll give you some of the principles that arise. So, for example, when you use an interrupt service routine, you're writing concurrent software. Concurrency is tricky. in software because of the abstractions we use for software, not because of the mechanics of C programming. That's uninteresting, and it's not the key principle. The key principle is that programming is based on an abstraction, which is imperative logic. Step 1 follows step 2, follows step 3. Well, actually, usually the other way around. Step 1 precedes step 2, precedes step 3. And each of these steps updates variables, right? And this sequence of steps is kind of the principle we use to build software. The physical world doesn't work that way for the most part, okay? In the physical world, what's going on around you isn't step 1, step 2, step 3. It's all kinds of stuff happening at once and interacting, okay? The way that we emulate that kind of concurrent interaction in software is actually very poor, okay? The technology we use today is very primitive, in my view. It will be better. Probably by the time you're my age, it'll be completely different from what it is today. And it would be unfair for us to just teach you the tips and tricks of how to use what's there today without focusing on the principles. Because if you learn the tips and tricks of how to use what's there today, great. You've learned to use a rather poor technology that will be obsolete as fast as we can possibly make it obsolete because it's really crappy stuff. Okay? So we don't want to do that, right? But on the other hand, we want you to get the hands-on experience and actually do stuff, right? So you have to grapple with the stuff that's there today, with all its warts. Okay, in the lab, you're going to get the experience of playing with stuff that is pretty immature. You're going to run into lots of problems. You're going to get to be an engineer, right? Which means you're going to scratch your head, having no idea what's going on with this thing, and you're going to have to use some cleverness to try to figure out why it's not working. Okay? This is not going to be the kind of course where you just go to the TA and say, doesn't work, it's your fault. Okay? That's not going to work. The TA is going to say to you, you're an engineer, you figure out why it doesn't work. Okay? That's what you're going to have to do in the lab, actually. Okay? And that's also, that's kind of what the real world is like. Okay, so let me switch over to the content of today, which is primarily what we're going to do is we're going to start with the modeling of the physical world. Okay. Oh, by the way, let me just back up 1 second. Go back to the web page. This is the map. As I mentioned, this is the map of the course. Okay. It will evolve. Okay, but there are. We'll try to keep links to any PowerPoint slides that we use current here. But if you follow the links for lectures that are in the future, don't count on them actually being the same by the time we get there. We're trying to do continuous improvement here. But I strongly encourage you to set aside an appropriate amount of time to just sit and read. Okay? And it takes, some time of just sitting and reading. And so here are some guidelines, basically in 2-week chunks, about what you should read. And let me show this to you in pictures, actually. If you go to the Lee and Seshia website and follow the structure link, here is a map of the textbook. Okay? And this textbook is meant to be read concurrently. There are 3 threads, okay? Modeling, design, and analysis. And we would like you to start by reading chapter 2 and 7. You should read chapter 1 too, which is, kind of explains why we're doing all this, okay? But that's, that should be easy reading, should be kind of fun, read it at bedtime. Hopefully it won't put you to sleep, but if it does, at least you'll get some sleep. The technical content that you'll need for the problem set is in chapter 2, okay? We're deliberately not giving you problem set assignments based on chapter 7 because we've decided that, well, we can't do all of these topics in a lot of depth, okay? And so we're not going to do the topic of Chapter 7, which is the architecture of embedded processors. We're not going to do that in much depth at all. But it's useful to know, right? So skim it, right? Look at it, try to get a sense. It tries to give you a sense of where the state of the industry is today. But you don't need to spend a huge amount of time on it, okay? In the second week, after you've finished this, so we're kind of allocating 2 weeks for you to read chapters 2 and 7 and for us to cover the content here. We're actually going to get a little ahead of that in the lectures. We're going to start in next week on the contents of chapter 3 and the contents of chapter 8. Chapter 8 is essential, actually, to being able to get anything done in the lab with microprocessors. Okay, you do have to understand memory architectures in order to get anything done. So you will want to read that one in some depth. The next step will be to read chapters 4 and 9. So basically for the first 6 weeks of the course, we're focusing on modeling, which is shown in yellow here, and design, which is shown in blue. At that point, once we've got enough modeling, we can start to do analysis of those models, okay? And so at that point, we're going to kick in and start using systematic techniques for analyzing models and designs, okay? And then we switch into more of a focus on the analysis techniques. Okay. So today, I'm going to start talking about the content of Chapter 2. And I just wanted to first begin with just this notion of, what is modeling, design, and analysis? Okay, so what is a model? Well, there's model in the vernacular. Model, the word model is used in a lot of different ways. It's used to, someone who shows off clothing designers' latest creation, right? Or someone who sits for a portrait for an artist to paint. Or a plastic miniature car used to show management what, this concept of what the iCar is going to look like when Apple makes cars, right? Something, right? So a little plastic model, right? Something like that. So models are used, the term model is used for a lot of different things, but they all really share one thing in common, right? Which is that the task of modeling is a task of gaining a deeper understanding of a system through imitation, okay? So your goal is to imitate it. And so in a sense, if you're looking at a dynamic system, so for example, think of trying to design a truck that will not, swerve into oncoming traffic, okay? What is the kind of model you need? Well, you need a model that gives the behavior of the truck dynamically over time, okay? How does the truck react to a turning of the steering wheel, okay? That model is a description, okay, or an imitation, in a sense, of what a truck would do in the physical world, okay? The model itself is the artifact that does the imitating. Okay, the goal of a model is to imitate. Okay, and there's lots of different ways you can imitate. You can imitate statically if you're just a little plastic model that's showing the shape of something. Okay, that's an imitation. You can imitate dynamically, which means that your model moves the way your physical system moves. Okay, in software, we can use models which are computations that imitate the way a physical system moves, right? They imitate it by giving some description of what's going to happen when the steering wheel gets suddenly jerked to the left. Okay, so in that sense, a model will specify what a system does in reaction to particular inputs. Okay, so what is design? Well, design is structured creation of artifacts. Okay, so when you do a design, you're specifying how some task is accomplished. Okay, so when you write software, for example, you're doing a design. Now, by the way, you might be designing a model. Okay, so these things can get kind of intertwined. Or you might be designing a controller for a truck, okay, and using a model to assess your controller. How good is it? Okay? And of course, how good it ends up being in the physical world will depend a great deal on the fidelity of your model. So fidelity is kind of a key word here. And what we mean by fidelity is how well the model describes what the system being modeled is about. Right? You can build good models, you can build bad models. I could build a model of a truck that when you turn the steering wheel to the left, it flies up in the air. Okay? The fidelity of that model is not very good. Trucks don't do that. Okay? So we strive to get models that have good fidelity. And then once we have models that have good fidelity, we can design against those models with some confidence that those designs will then work when we deploy them in the physical world. Okay, so what is analysis? Well, analysis is the process of gaining a deeper understanding of what a system does through dissection. Okay, so this is teasing apart the pieces of a complex behavior and trying to figure out which pieces do what and what are the consequences of these pieces. So a very concrete example that we might have is suppose that we're designing a controller for a truck, right? And what we'd like to do is say, we'd like to be able to assert that if a certain sensor fails, that the truck will not on its own swerve into oncoming traffic, okay, without any input from the driver, okay? So one way that we might be able to assert that is by taking a design which works with a model, okay, of the truck, and doing an analysis of that design to look at all of the possible states that design can reach, okay? And then we look at the condition under which the sensor fails, and we say, okay, there's the set of states here that are problematic, the ones where the truck will swerve into oncoming traffic, cannot be reached by this design, okay? In a sense, if we can prove that the design cannot reach those problematic states, we've proved safety. Okay, now, we of course haven't proved perfect safety. You can never prove perfect safety about any engineered artifact. But you can prove safety with respect to particularly carefully stated conditions. Okay, if you can state the condition, the truck should not do blah formally, okay, and you can then prove that your design working with this model cannot do blah, you have proved a safety condition, okay? It doesn't guarantee that the system won't fail. You can never do that with engineered artifacts. They will fail, okay? But you can, in fact, prove that designs working with particular models don't fail in certain ways, okay? And that's a very useful thing to do. So that's what we do with analysis. Okay, so today we're going to focus on modeling, which is about developing insight about a process mostly through imitation. We're not going to focus so much on artifacts. So, modeling, if you build one of those plastic models of an airplane, right? You're not describing the dynamics of the airplane, you're describing its structure. That's very static. We're going to be interested primarily in models that describe dynamics, which is the change of state of a system over time. Okay? So we're also interested primarily in mathematical models. Now, why would we be interested in mathematical models? Why do we care whether the model is mathematical or not? Somebody want to comment about that? Yeah. The mathematical models allow for analysis. That's right. I mean, one of the key properties of mathematical models is that you can do certain syntactic manipulations on them that preserve truth, right? So if you have a formula that you believe to be true, you can do certain changes on that formula and conclude that you have every bit the same level of confidence that the result is still true. If your original thing was true, this thing is still true, okay? That ability to preserve truth through systematic manipulations is the value in mathematical models. More informal models don't have that property, right? If you have an informal model, it could be useful, okay? But you do a transformation on it, and you don't really have any assurance of preserving truth when you do that transformation. Okay, so that's why we focus on mathematical models. There's another reason for focusing on mathematical models, which is that it's becoming increasingly common if you're given a model that is mathematical in some sense, you can then synthesize implementations from that model. So you can generate C code, for example, rather than writing the C code by hand. Okay? Now, what are you doing? Well, when you take a model and you generate C code, you're doing a transformation. And the goal of that transformation is to preserve truth, right? If the model has certain properties, the C code will have the same properties. Okay? That's the goal. So some of you will probably want, maybe in your projects, you might experiment with the synthesis capabilities that LabVIEW has. LabVIEW is able to synthesize embedded C code from models, and it's also able to synthesize FPGA hardware designs from models. And the boards that we're going to be using in the lab have FPGAs as well as microprocessors on them, so you can synthesize software or hardware, and you can make that part of your project to explore those synthesis techniques. I should tell you right away that, in my opinion, these synthesis techniques are still at a very early stage. You will have problems using them. That you will encounter frustrations. But I also believe that this technology is very much the wave of the future and will get used a lot more in the future, so getting some experience with it could be very valuable. Okay, so we're interested in models that abstract system dynamics, but the word dynamics is a key term. Dynamics means how does a system state change over time, okay? And when we look at physical phenomenon, we often use ordinary differential equations, okay, to describe physical dynamics, or their discretized versions. So let's talk a little bit about those. So first of all, I want to say that if you're talking about modeling continuous dynamics of a system, so you're interested, let's make this very concrete. We're interested in how does a truck behave when the steering wheel turns. The steering wheel is a rotational motion on a mechanical device, right? It's a torque applied by a driver, okay? And then there's some chain of possibly mechanical, or in today's modern vehicles, it's actually a sensor, a computer, and then an actuator somewhere else on the network that will actually turn the wheels, okay? They call that X-by-wire, drive-by-wire in this case particularly. Drive-by-wire car is one where there's no mechanical coupling between the steering wheel and the devices that cause the wheels to turn, okay? Instead, there's a sensor on the steering wheel that tells a computer how much the steering wheel was turned, and then there's an actuator on the wheel that tells the wheels how much to turn, okay? That's drive-by-wire. Understanding the dynamics of that interaction, and then once the wheels turn, what happens? Well, it's kind of complex, right? The vehicle has inertia. It doesn't want to turn, it wants to keep going straight, right? Newton's first law, okay? So what's going to happen? Well, the first thing that's going to happen is that there's going to be a lateral force applied by the friction between the tires and the road surface, okay? If you really want to understand the dynamics, you need to understand the friction. You need to understand how the tires behave, right? If they have this lateral force, they are going to bend, right? Tires are flexible. That will change their dynamics, okay? They'll apply a force on the wheels. The force on the wheels will try to pull the truck over. By the way, it's pulling it down very low, close to the road surface, at the road surface, in fact, okay? So the inertia of the truck could, in fact, lead to the whole thing tipping over, okay? Because you're applying the force at the road surface, okay? So you got to be careful about that. You don't want the thing to tip over if you're turning the vehicle. Okay, so you've got to understand those coupled dynamics. Now, you know, some of you are mechanical engineers, I know. You say, well, duh, that's what our whole program's about, right? Yeah, and that's right. And you don't need to be a mechanical engineer to take this course, okay? And in fact, for the mechanical engineers, the stuff in Chapter 2 is boring, right? You've seen it before, you know it, easy. So buddy up with a mechanical engineer if you're having trouble with it, and they'll explain it to you, okay? You don't need to know it. We're going to treat it at a very superficial level because we want you to be able to use these kinds of modeling techniques. Again, a superficial level is fine, right? The dynamics of the robots that we're going to use in the lab are very simple. You don't really need to get very fancy. You don't need to worry about the friction of the wheels. You could, by the way, maybe in your project you'd like to, study something like that. One of the projects last year made an application where you draw a sketch on a tablet, and a robot moves around and with a pen in its hand and draws the sketch on a piece of paper taped to the floor. Didn't work very well, right? They would draw a star, and the star would come out, without the points being connected, because there was friction that was, giving them non-ideal behaviors, and so they actually spent a good bit of the effort in the project trying to improve their model and thereby improve the mechanism by which they were controlling this robot. And they actually they made some pretty significant improvements, and they got it to be a lot better than it was in the initial try. Okay? But in any case, the subject of modeling continuous dynamics is a deep subject that you can go on, and take very advanced courses. So advanced courses graduate courses in model predictive control, right, are all about, controlling these kinds of physical dynamics. But we're not going to do anything that fancy. Let's stick to things that are really pretty simple. So I'm going to illustrate some points by talking about a helicopter, okay? And this helicopter is a simple one. It's got a single main rotor on top, and it's got a tail rotor in the back. Why is there a tail rotor in the back? Yeah. Sorry? To counter the torque from the main rotor, right? So the main rotor is spinning, okay? And there's a motor driving it to spin. But of course, what's going to happen if there's no tail rotor? Well, the body of the helicopter is going to be able to swing arbitrarily, right? And because of friction, it's going to tend to want to swing in the same direction that the main rotor is going, okay? And eventually, the helicopter is going to be, flipping around at the same speed as the main rotor, and it's going to crash. Have any of you seen the movie Black Hawk Down? Okay, it has a sequence that shows exactly that happening, right? Where a rocket-propelled grenade hits a tail rotor on a helicopter hovering over Mogadishu, and it crashes, right? And you can actually, the video is extremely realistic. It shows you exactly how the swinging of the body causes loss of control of the helicopter, which brings it down, okay? So let's just focus on, all right, we need to design a system, and we're going to do a fly-by-wire system for this helicopter, okay? By the way, traditionally, these were not fly-by-wire systems, right? But today, they always are. Does anybody know why? Why would aircraft manufacturers be switching completely to everything being controlled through networks rather than through hydraulics and mechanical linkages? Yeah. Hydraulics are big and heavy. That's exactly the problem, right? Wires are not so big and heavy. By the way, the weight of the wires in a lot of these aircraft is a problem because they're using rather sloppy techniques for the networking, and they put in way more wires than you'd like to, okay? But that's partly because the technology hasn't progressed well enough to give us networks that are reliable enough to give the behavior that you need to be able to safely control these aircraft, okay? But nonetheless, even big bundles of wire are much lighter than hydraulic tubes, okay? And as a consequence, you can dramatically reduce the weight of an aircraft. In fact, Boeing estimates that when they switched, the Boeing 777 was the their first fly-by-wire aircraft, and they estimate that by switching to fly-by-wire, they reduce the weight of the plane by 30%. Okay, so that reduces the fuel consumption by about 30%. Okay, so if we want to understand how to do a fly-by-wire system on this, we need to understand the dynamics of this system. Okay. And in a simple model of physical motion, we talk about having 6 degrees of freedom. So you have an object in 3-dimensional space, so it has a position in 3-dimensional space. We could call this the XYZ position, where by convention X is horizontal, Y is vertical, and Z is towards you or away from you. I mean, the sign can vary, but that's kind of the convention that people tend to use. But in addition to position in space, you have to talk about orientation. You know, is the helicopter pointed in the X direction, or is it pointed in the Z direction? Okay. So we use pitch, yaw, and roll to model the orientation information. And these terms are actually defined by an aircraft that has a distinct front end, okay? And a roll means this, okay? The wings are tilted. That's roll, okay? Pitch is this, okay? You're pitched forward or you're pitched backwards, okay? And yaw is this, okay? One of the interesting things about aircraft is that if you land a plane in a crosswind, what is the yaw relative to the runway? Yeah. Yeah, it'll be turned into the wind, okay? That can create a pretty interesting problem when the wheels hit the ground, okay? Because what's going to happen? Well, if the wheels are pointed in the forward direction on the aircraft, you're going to get a pretty strong lateral force due to the friction of the tires on the runway, okay? So landing planes in crosswinds requires understanding that dynamics, okay? Okay, so pitch, roll, yaw, position, 6 variables that vary over time, okay? That's why they're called 6 degrees of freedom, okay? The orientation, pitch, yaw, and roll are angle measurements, okay? X, Y, and Z are distance measurements in meters, okay? Now, I want to take a little sideline here and talk a little bit about notation, and I'm going to try, because this is being screen captured, I'm going to try to use a technology that I haven't tried to use before in classes because I really like blackboards, but they won't get screen captured, and so they won't be that useful to you later on. So I'm going to attempt to use this to get the effect of a blackboard, okay? Feel free to interrupt me with questions or comments, okay? But so when I talk about the position of an aircraft in X, Y, and Z, what is X? Okay, so I've just given you kind of a very informal thing. I'm just going to talk about the position in the X direction. So tell me mathematically, what is X? Sorry? Somebody. How about you? It's a vector. Well, actually, that could be, but let's say that X, Y, and Z together are going to be my vector. Okay, so the X will measure my position in the horizontal direction. Y will measure my position in the vertical direction. Z will measure my position in, out of the screen. Okay? So then I could form a vector by putting those 3 together. Okay? But the question then still stands, what is X itself? Yeah. Distance from the origin along the x-axis. Yeah, so if I have if I draw a 3-dimensional space, right, I've got X, Y, and Z, and I've got this thing somewhere positioned there, then x might be how far along I am in that direction. Now, this sketch suggests that x is a real number, right? Right, x is a real number, okay? So if x is a real number, then the position of an aircraft is going to be 3 real numbers, okay? So I might have the aircraft at, 0.1 meters, 9.6 meters, and 12.3 meters from some origin, okay? So that's great, but how am I going to use that to describe dynamics, right? Dynamics is how the state of a system changes over time. So now, well, okay, now I have to realize, all right, that's the position at a particular time. So it's not actually, if x is just giving me the position at one time, then x is not going to be useful to describe dynamics, right? X has to give me the position over time. So how should I change x so that it can give me the position over time? Yeah.
You need to add on an x dot times t and 1/2 x double dot.
Yeah, so by the way, I'm going to try to repeat what people say because it's more useful in the screen capture. So you gave a good intuitive answer. You're going to want to describe an x dot, okay, which is the derivative of x with respect to time, okay? If x is a real number, what does this mathematical expression mean? Oh, sorry. So if x is a real number, what does this mathematical expression mean? dx over dt. Actually, it's nonsense. It doesn't mean anything. You can't differentiate a real number. Yeah, you can differentiate a function. You cannot differentiate a real number, okay? This is not a well-formed expression. Okay? I'm going to be a bit of a stickler on the notation here because one of the interesting things about working with cyber-physical systems is you can get very confused pretty quickly if your notation is sloppy, right? If you don't know what the variable x actually represents, you can prove some amazing things, but they don't end up actually being true. They don't have good fidelity, okay? So we have to be careful with notation, okay? So if we want to be able to differentiate this variable, let's start over. Let's say x is, I got to scroll back up now. X is not going to be a real number anymore. In fact, x is going to be a function that maps real numbers into real numbers. Okay? Now, by the way, I've made an implicit assumption here that I'm going to model time as a real number, right? So if I have a time t that is a real number, okay, then what is x of t? Well, that is itself a real number, okay? What is x? X is a function, okay? And the notation we use is that x is a member of a set of functions that we can write as the set of all functions that map real numbers into real numbers, okay? That's one notation. Another notation you see commonly in the literature is that, r to the r, okay? But I'm going to tend to steer clear of that notation, okay? But it's worth knowing that it is there. So a set of functions will be shown as this parenthesized expression, okay, with an arrow. So the point is that the variable x here is not a real number, it's a function. So it's a member of a set, like any variable in a mathematical expression. A variable in a mathematical expression is meant to represent a member of a set. What set? Okay, it's important what set. And in this case, it's a set of all functions that map reals into reals. Okay, so now we can, in fact, take a derivative we can talk about dx dt, okay, which we can also write as x dot. What is x dot? Okay, it's a mathematical symbol. Is it a real number? It's also a function. Okay, x dot is a function that maps reals into reals. Okay? So let me just emphasize here the notation that I'm going to be using, okay? So in general, we're going to talk about a function having a domain and a range, okay, which we write like that. F is you read this as f is a function that maps the set D into the set R, okay? You can write f is a member of the set of all functions that map D into R, okay? You can write that for all members of the set D, f of D is a member of the set R. Okay? What else can we write that would be interesting here? Well, I guess that's about it. Okay? So in this case, when we talk about position, okay, x is a member of the set of all functions that map reals into reals, where I'm assuming that I'm going to model time as a real number, okay? I don't always do that, by the way. In software systems, what is time? Yeah, well, it's probably, first it's discretized, right? Because computers don't deal very well with real numbers, right? If you ask your computer what is the current time, the answer at its core is it tells you how many seconds have elapsed since January 1st of 1970. Okay? That's what it tells you. And that's an integer. Okay? That's a model of time. But is it actually a model of time? If I ask my computer what time it is, and at the same instant you ask your computer what time it is, do they give the same number? Nah. They can't actually. I mean, they can't actually be perfectly precise, right? So in a networked system, the components in the network will disagree about what the time is, right? And consequently, it's kind of a mistake to think of a single variable representing time in an interesting embedded system. You have to be much more careful about what time actually is in this system and how it's measured, okay? All right, so what about pitch? Okay, we have roll, pitch, and yaw. So what should pitch be? So one suggestion is that pitch is a member of the set of angles. Okay, which we could say, all right, let's pick radians. So this is the set ranging from 0 to 2 pi non-inclusive. Okay, so this notation means a range of real numbers starting at 0 and including 0, up to 2 pi but not including 2 pi. Okay, that would be one possible way to represent angles. Is this a good choice for a model for pitch of an aircraft? Well, it sort of suffers from the same problem that we had with X. It's not going to be very good at describing dynamics. Okay? Yeah, so let's instead do pitch is a member of the set of functions that map real numbers into angles. Oh, thank you. Okay? So pitch is a member of the set of functions that map real numbers into angles. Okay? And now I can use pitch to describe dynamics. Okay? This choice of a measurement for angles has potential problems, right? What can you imagine would be a potential problem with a mathematical model that uses this kind of a function to represent pitch? Someone want to? Yeah. Yeah, there's kind of an intrinsic discontinuity in this, right? By which we mean we can have perfectly continuous behavior. Imagine the helicopter problem, right? The tail rotor rotates around, and it's maybe rotating at a steady rate, okay? Perfectly continuous behavior, but our function has these discontinuities that are going to jump by 2 pi, okay? Those discontinuities are a property of the model, not of the physical system, okay? There's a potential fidelity problem, right? If you take these angle measurements and feed them into a linear time invariant system to filter them, those discontinuities are going to show up as artifacts, which are going to wreak havoc on your controller if you don't do something about them, okay? These are the kinds of problems that an embedded system designer has to deal with. You have to choose a representation for the physical quantities you're talking about, and then you've got to live with the consequences of your choice, okay? And often you're faced with a situation where no choice is perfect, okay? You're stuck with an imperfect choice, and you have to live with it. And so you need to understand your model in detail in order to understand where the potential problems are that are going to arise. Okay, so let's go back to PowerPoint. So now we can give position by 3 functions, or we can more conveniently collect them into a vector. Oh, so let me just actually go back here a second and talk a bit about vectors. So if I have x, y, and z are all members of the set of functions mapping reals to reals. Whoops. Okay. I could collect them into a vector, x, which I might write like that. Okay, and now the question is, what is this bold x or underscore x? Well, this is a member of the set of functions that map reals into reals cubed. Okay? What is reals cubed? Well, a member of the set reals cubed, this means for all times in the reals, x of t is a member of the set reals cubed. Okay? And a member of the set reals cubed is, so for example, I could write x of t as a variable x1, a variable x2, a variable x3, okay, organized as what we call, this is called a 3-tuple. Okay, just a collection of 3 variables, okay, and that's simply a member of the set R cubed. Okay, so that's just notation that is hopefully not unfamiliar, but it's, you know, worth just going through it just to make sure everyone's on the same page. Okay, so now going back to the PowerPoint, we can see that we can represent the position as a bold function x that maps time into R cubed. Okay, and now we can start to do operations on this that are fairly compact. So x dot, which is the derivative of x with respect to time, in this case will also be a function that maps the reals into R cubed, okay, simply the derivative. The acceleration is x double dot, okay, and we can model the force on an object as a function that maps reals into R cubed. Why R cubed for the force? Sorry? Right, there's going to be 3 components of the force. There's, for example, if you're an aircraft, there's gravitational force, there's a lateral wind force. You know, these are forces that are applied externally to the aircraft from the outside world. There's the lift force, which is force on the wings, okay, in the vertical direction. So the force will be a function from R to R cubed. And we can take Newton's second law, which, by the way, all the physics you need to know to do modeling for this course is F equals ma. Okay? That's enough. We're not going to do anything fancier than that with differential equations. So if you know F equals ma, you're all set, okay? So what is F equals ma? Well, it says that a vector of forces at time t is equal to the mass of the object times the second derivative of the position. Okay, so that's what that first line says. Okay, so that's F equals ma. So the problem with that first formula is that it doesn't account for initial position and initial velocity. So you can integrate both sides and get an equivalent expression, which is shown down here below, where x of t is equal to the initial position x of 0 plus the amount of time that has elapsed since you were at that initial position times the derivative at that initial position, which is the velocity, the initial velocity, okay? And then you have a double integral of the force over time scaled by the inverse of the mass. Okay, so that's just integrating this expression on both sides twice. Okay? So how do we translate this into orientation? Okay, so the force that is applied to the aircraft here was a three-dimensional vector. So it's getting pulled down, pushed to one side, pushed to the other side, okay, by some three force components. Okay, what about twisting forces? Okay, you can also have twisting forces, all right? So those are simply called torque instead of force. A twisting force will be called torque. F equals ma still works, except it becomes torque is equal to moment of inertia times angular acceleration, which you might write as, I don't know, a sub theta. Okay? So your rate of change of angle, the second derivative of your angle versus time, which is the angular acceleration, multiplied by the moment of inertia. So this should be, I use a different symbol. Moment of inertia is equal to the torque, which is the rotational force. Still F equals ma. It's just translated into a frame of reference that is about rotation, okay, rather than about linear acceleration. Okay, so we can talk about the orientation of an object being a vector theta, a vector function theta, that at a particular time gives us the pitch, roll, yaw. Okay, the first derivative will give us the angular velocity. The second derivative will give us the angular acceleration. The torque is a function that also is rotational yaw, rotational pitch, and rotational roll. Let's see, did I get that right? Yeah. So rotational roll would be the force that makes it, the wings roll. Rotational yaw is the force that makes the wings, one wing move forward relative to the other, and rotational pitch is the one that makes the nose of the aircraft point up or down, okay? And there's forces applying those things, okay? So now, for this helicopter problem, we can actually simplify things considerably because we can change our whole frame of reference to be the helicopter itself, okay? All we need to do is keep the tail from rotating when the top rotor is rotating, okay? So we can change our frame of reference so that the frame of reference moves along with the helicopter. And that makes things a lot easier because now we can just have a scalar equation which says that the torque around an axis. So here's the main axis of the helicopter. So think of this big mass here as representing the tail of the helicopter, okay? We apply a rotational force on that. There's a moment of inertia that depends on things like how long the helicopter is, okay? It's very helpful, by the way, to have it be relatively long because then a relatively small rotor on the back will be more effective, right? And this formula will actually kind of tell you why, because you can figure out that the length changes the moment of inertia, all right? But in any case, you get this simple expression where the torque as a function of time, now a scalar, okay, is equal to this moment of inertia times the rotational acceleration. okay? The three-dimensional version is more complex, but it's a similar idea, and we're not going to worry about the three-dimensional version. We're going to stick to the one-dimensional version where the frame of reference is just simplified. So here it is. This is the yaw dynamics. So what we're interested in, the position of the tail of the helicopter is yaw, right? Just pure yaw. We don't care about anything else, just yaw, okay? So the whole thing becomes a scalar. We're interested only in the moment of inertia with respect to that yaw, okay? And the rotational acceleration for that yaw. And we now have an expression just like F equals ma. We can integrate it once and get an initial rotational variable. We could integrate it twice and get an initial angle as well. Okay? So now the goal is to design a feedback controller that will stabilize the position of the tail of the helicopter relative to the position of the shaft. Okay. So I'm seeing that it's warm. Having some trouble dealing. Shall we take a 3-minute break? Everybody stand up and stretch your legs. We got about 15 minutes left to go, but I think it might be helpful to just let's take a little stretch break because this room is not ideal. Oh man, opening the door helps a lot. Maybe we should leave the door open. It's so much nicer. Yeah. Let's do that. Let's just that. I don't know if that's going to work. There we go. Yeah. Wow. Okay, that's 3 minutes. So let's go ahead and resume. We don't have much more to do today, but let's resume, please. So what I've given you so far is a little review of physics, which most of you took in high school, F equals ma. My point isn't to review physics. We don't care that much about the physics. The point is that we have constructed a model, okay? And that is actually the key thing that we're interested in, is that when we write down a differential equation like this, that the yaw dynamics is given by this equation, we have constructed a mathematical model against which we can now design a controller. Okay, we can design a controller that will work with this model. Now, the controller, when we put it on the helicopter, if we just use this model, it's not going to be perfect, right? Why not? Well, because this model doesn't take into account the fact that the tail of the helicopter flexes. Okay? That's completely ignored in this model. Okay? It might be important. It might not. You don't know, right? But the issue is that you could design a controller that has, for example, chattering behavior. That it stabilizes the helicopter, but the tail wiggles like a fish. Okay? And if you're Sikorsky, you're going to have trouble selling that helicopter. Okay? And the consequence, this may be simply that your model isn't good enough. The fidelity of your model isn't good enough. Your controller may be perfect for the model, right? But its fidelity isn't good enough. So you always have to keep in mind that you're doing designs against models. You are always doing designs against models, by the way, unless you're just hacking, right? So in fact, maybe one of the key things we're trying to get at in this course is you're doing designs against models. If you're not doing that, you're hacking, which is trying it, seeing what it does, trying it again, seeing what it does, tweaking some parameters, seeing what it does, without developing any principles, right? By the way, the trying and seeing what it does is a useful process, but what it should do is help you refine your models, right? Rather than help you refine your designs. You should refine your models by understanding what it does, measure what it actually does, refine your models, improve your designs against the models, okay? Then make new measurements, refine your models again, okay? That's the process that we want you to be doing, as opposed to just trying stuff and seeing what works, okay? And the reason for doing that, by the way, is that you can actually do designs by just trying it and seeing what works. But it's not a very good technique. And if you're competing with people who are using a smarter technique, they're going to do much better designs than you did. Okay, that's the key point. Okay, so we have a model. Now, I'd like to give you a twist on that model, right? The model that we've seen now is a formula that describes a differential equation, okay? But cyber-physical systems are compositions of a bunch of components. How do we connect them together? Well, one way to do it is we, write down a lot of differential equations for all the different components, and then we, write down equations that describe all the interconnections between these things. And pretty soon we have a big mass of equations that can be very difficult to understand, okay? You lose sight of what are the components of the system, and how do the components fit together, and how do the components interact, okay? So we use these kinds of mathematical models, these differential equation models, in combination with what we call actor models. So an actor model would look something like this. It's a system, a box, that has as an input x and an output y, where x and y are both functions. Okay, so in this case, we have, for example, an input x that is a function of time, an output y that is a function of time. The system takes an input function and gives us a new output function, okay? Where capital X and Y are sets of functions. So the system is a function also in this case, but its domain is a set of functions and its range is a set of functions, okay? If you have any trouble reading this, please read Appendix A in this book, okay? It's, some people just, you haven't gotten the notation in quite as rigorous a sense, and so, it's worth it. It's a short appendix, and it just goes through the notation very carefully, okay? But now we can talk about a component, and we can interconnect components. So, for example, the helicopter, with our simplified one-dimensional version of the helicopter, could be described as a component that takes torque in and gives us angular velocity out. Okay? So what are we modeling here? Right? When you crank up the tail rotor, you give it more gas, okay? What you're doing is increasing the torque on the helicopter, okay? So the gas that you give to the tail rotor is this signal. It's proportional to this signal, okay? So this is the throttle to the tail rotor coming in. And this is how the helicopter reacts to that throttle. How does its angular velocity change? So now we have a model against which we can do a design. We can measure what the helicopter is doing, okay, and figure out how much gas to give to the tail rotor based on what the helicopter is doing. So we can create a little feedback system that takes a measurement of the angular velocity and uses that to control the tail rotor. This is exactly how helicopters work. They measure the angular velocity, and they either crank up or crank down the tail rotor. If it starts to swing this way, you crank it up to push it this way. If it starts to swing the other way, you crank it down so it's not pushing so hard. Okay? And you just do this in a continual feedback loop. Okay? So this helicopter itself, of course, we could break down into a more detailed model. So it could have a single component that just scales the input and then integrates it. That is, of course, just a representation of that integral equation that we wrote down before, okay? But it's a representation in pictures, and these pictures are a little bit easier to compose into systems than the equations by themselves, okay? So one of the reasons that we use LabVIEW in this course is that it is a representative of, there's a bunch of tools out there that are kind of like it. Some of you have probably used Simulink, which is like it. There's a bunch of others as well. It's a representative of a set of programming models that describe systems in this way, as interconnections of these input-output components. And it's a useful way to build up complex systems from simpler components, okay? And it's a way of modeling. It's a modeling technique. So we can have systems that have, for example, a pair of inputs. So what is that? Well, that's, for example, a function that takes a two-tuple of functions and gives us a function, okay? So for example, I could have an adder that takes a function of time and another function of time, and at any given time adds the two values and gives me the result, okay? And I want to show you the notation here. If the system S is this adder, okay, then it is a function whose domain and range are sets of functions. So S of x1, x2 is a function. Notice the notation carefully. x1 is a function, x2 is a function, okay? And x1 comma x2 in parentheses is a two-tuple of functions. You apply the function S to that two-tuple of functions, the result is a function, okay? That function is wrapped in parentheses here and can be applied to an element of its domain, which is time, okay? So notice the notation carefully. We're being very careful about what the symbols mean. Do they mean functions or do they mean real numbers? Everywhere here, we're being very careful to use them only in ways that are consistent with what they actually mean, okay? And the whole reason for doing that is to avoid confusion, okay? Because you mess up if you use a symbol, if you define a symbol to mean one thing and you use it a different way, you draw conclusions that are simply false. And it's easy to do. Okay, so here is a simple feedback controller that will control the helicopter, okay? It takes a measurement of the angular velocity and it subtracts that from the desired angular velocity, okay? If you're trying to just hover the helicopter, the desired angular velocity is a constant function 0. You don't want it to rotate, okay? So phi here is a function that at all times has value 0. So what we're doing is we're taking our measurement of the angular velocity and comparing it to 0. If the helicopter is moving, is twisting, then E will be non-zero. We will multiply that non-zero by a constant and apply gas to the tail rotor. Okay? The polarity of this constant is really important. What do you think happens if you get the polarity wrong? Yeah. Right, the system becomes unstable, and your controller actually makes the problem worse rather than better, right? So you got to get the polarity right so that you're correcting rather than exacerbating the problem, okay? But this principle of measuring the error against what you'd like, taking that error and using it to correct is a very simple principle, and it's very, very powerful. You're going to do this in the lab to design robots that will sense when they're on a hill and figure out how to get themselves to the top of the hill. Okay? It's a simple enough problem. Okay, so you can use that to study the behavior. There's other modeling techniques we're going to talk about, but this one is enough for now, so this is a good place to stop, and I'll see you on Tuesday. And I am going to get after the TAs right now to do something about getting the lab sessions organized.